Hello everyone, I am here with another interesting topic related to distributed systems, and it is about RAFT protocol. If you are learning a distributed systems or you are already in distributed systems, then RAFT might be one of the interesting topics for you. So let's get started. What we are going to learn, we are not just going to learn distributed consensus as a RAFT, but we are going to learn leader election, log replication, leader, follower, candidates, timeouts like heartbeat and election timeout. They are actually the subtopics of RAFT, but we are going a lot of interesting stuff in this tutorial. So let's get started. First, let's try directly to start from our problem domain. So what we have a single node system. It means we have one single server. Okay, and we have a customer. Our user wants to store some information in this database. Okay, the user is going to insert some card information to our database. In this case, if we have success operation, user will be notified about success information. Otherwise, if system fails, we'll get the failed information or some type of exceptions or etc. So agreeing on some value or consensus is easy for us when we have only one single node. It means you have only one single server. There is no need to check with other servers that, guys, what is the latest value in your system, and agree on some value. We have one single server. We have one single source of truth. That's the easy thing to implement in a single node system. This is actually called the consensus. So what if we have a distributed system? In distributed system, we have a cluster consists from multiple nodes. It means we have one single huge server that acts physically like multiple servers. Okay, so these multiple servers acts as a one single server. So we are going to insert some information to our cluster, and the user will interact one of these servers called leader server, and the leader server will replicate data to other followers. We'll talk about leader and follower, but for now, just understand that in our distributed system, we have added additional attributes like fault tolerance and data distribution. Data distribution means we have the same information in all servers. Fault tolerance means if one of the servers fails, system will continue working without issue. If you have 4 nodes, 4 servers in this case, and one of them fails, and the other 3 servers will continue working without any issue. This is actually called fault tolerance. Okay. What is the actual problem here? The problem here is if user is going to add multiple operations, user is going to do multiple operations. It means user is going to do manipulation operation like insert, update, delete. In our case, we have 3 inserts, but in our servers, we have different values. Let's see, we have in node 4 all these 3 values like 12, 25, 30, because in distributed systems, we have a single source of truth, and it is called log. So every operation is a log in our system. Okay, in our server, we have 3 logs in node 4. In node 2, we have 2 logs. In node 3, we have one single node. It means somehow replication failed in node 3 2 times, in node 1 1 times. Okay, in this case, we have 2 different last value. In node 3, we have 12, in node 2, we have 25, and in node 4, we have 30. So which one is a valid value? So this is actually going the most important problem in our distributed systems. Agreeing on some value in this case actually call it distributed consensus issue. Okay, this is what RAFT is trying to solve. RAFT in a multi-node system. So we have leader node. Leader node means we have a users, and users will always interact with a leader. In one cluster, it is possible to have only one leader. The other servers will be our followers. Our leader will replicate data to our followers, and the user will interact only the leader. Okay. But how did we get to this point? This is actually the final snapshot from the RAFT. But let's try from scratch understand how the system, how the implementation ends with this image. So RAFT is a distributed consensus algorithm. Okay, we need to agree on some values in our distributed system. Consensus is a fundamental problem in our fault-tolerant distributed systems. It means you have multiple servers and we have different values in multiple servers. We have only one single source of truth. It is called log, but we have different logs in our different servers. So we need to understand which value is true, is the latest value for us. RAFT is a protocol for implementing distributed consensus. We'll dive into details. Let's get started. So the first things first, everything starts from the leader election process. We have 4 nodes, okay? None of them is a leader. We have 4 nodes as a 4 followers. They are actually stored as a follower, okay? We don't have a candidate. We don't have a leader. We have 4 followers. For followers, we have, per follower, we have timer. Okay, and the timer value randomly generated. So it might be from 150 to 300. Okay, we have 170 in node 1, in node 4, node 2, node 3, we have different timeout values. It means when timeout ends, for example, node 1, this is the least value in our servers. Node 1 is going to be our leader because it has the least value for timeout. Okay. The election timeout, it is called actual election timeout. Election timeout is a follower timeout that waits for a follower to become a candidate. Okay. The election timeout is randomized to be between 150 and 300 milliseconds. Nodes will wait for a new election and try again only if we have multiple candidates. Let's talk about these candidates. So you see we have different color here. It means for node 4 and node 1, we have the same timeout. They are ending up at the same time. Now we have 2 candidates for a leader. So which one to select? If when we start everything, we don't have any value, any logs, so the system will try to do the election process again. So for node 4 and node 1, we will have a different value again. So the process starts from scratch. Okay, let's say for node 1 the timeout finished before the other followers, and now node 1 is going to be our candidate for a leader. Okay, this candidate will send to the followers a request. First, the node 1 will vote for itself, and then we'll send to other followers that, guys, please select me as a leader. Okay, and all other followers will respond that, okay, go ahead, you are a leader. And now our node 1 is going to be our leader. Cool. The responsibilities of leader is below. We have leader. Our users will interact only with a leader. Okay, and the other responsibility of a leader is actually replicating data. Okay, but how we are detecting that we are not going to have another election process? So our leader will, depending from the configuration, will periodically send some signals, some requests to other followers that, guys, I am working, everything is okay, no worries, please don't go to another election, actually. Okay, and for the nodes, you see, we have election timeout. Still, it doesn't matter if we have a leader or not, we always have election timeout because it is possible for node 1 just fail. And in this case, we will go to another election process. So long story short, we have a leader, we have a followers, and our user will interact with a leader. Leader will replicate data to the followers, and if we're using this replication, we should have the latest value for all servers. That's the actual solution. Okay. The first leader means the first term to be started. So our first election process ended with node 1. So node 1 is going to be our leader, and our term equal to 1. This is some type of attribute in our distributed system. It means we have only one selection right now. If we are going to another election, at the end, we will have term equal to 2. Every selection will increase the term count. Okay, in general, what we have? We have 3 states in our nodes, okay? We have a leader, we have a candidate, and follower state. When everything starts, we have only followers. When timeout ends in one of the blockers, we have a candidate or candidates. It is possible. It is possible to have multiple candidates, multiple followers, but only one leader. Okay. All clients interact with the leader, and leader replicates, sends logs to the followers. Let's talk about log replication process. We have a client here. Client sends information to node 1. It is not a single node system, so the information, the insert, update, delete, doesn't matter. The operation is not going to be committed. It is in like a staging mode, like in Git. It is appended mode, okay? It's called appended. And our node will replicate this information to other followers. Because our followers should store the latest entry, log entry. Okay, we have log consists from multiple entries. Okay, and in this case, our followers should respond to the leader that, okay, we got this information, go ahead. Every operation is a log for nodes. Clients interact with the leader replicates data to followers. That's all. So when we send this information to the followers, our followers should respond with okay to the leader, and only in this case, leader will commit this information. If the majority nodes return okay, then commit. This is the actual simple logic in our leader. After commit, leader will send additional requests to the followers, because in our followers, we have, for this log entry, we have state appended, okay? And the followers, in this case, will commit in their side also. Okay, what if our leader fails? This is actually a possible case, and this is also resolved in RAFT protocol. So again, leader election. When leader fails, it means periodically leader should send some heartbeat signal to the followers. But somehow leader failed and fall down, and we don't have signals. The followers the followers are going to have another election process, and all these things starts from scratch. You have again timers for followers, and if one of the timers in one of the followers ends first, the following node is going to be a candidate. Candidate will send leader request, being a leader request to the followers. Followers will respond, and the candidate node is going to be our next leader. The leader election will start again with incremental term. It means if the first time when our node 1 was a leader, our term was equal to 1. And now we are going to another election. It means we are going to have a term equal to 2. Okay. And let's talk about one of the important things related to distributed consensus. It is about data consistency, okay? We have node 4. Node 4 has 3 entries in its log. And for node 3 and node 2, we have different amount of logs, and we don't have any log in node 1. Okay, how to deal with this issue, how to make our system to be consistent. Right now, our system is inconsistent mode. It means when node 4 fails, we don't have the last information in node 2, if node 2 is going to be a leader, or in node 3, we even don't have the last 2 information. Okay, let's talk about this data consistency and the solution for it. We have node 4 as a leader, and it has the fourth item, the fourth insert operation, okay? It is going to be term 1 index 4. So in our system, we have entries, and the identification for entries is going to be term plus index. So we have term 1 election, and we have indexes. It means some type of ID in our database, incremental ID, okay? For cart amount 12, we have index 1. For 25, we have 2. For 30, we have 3. And for 40, we are going to have 4, okay? So we are going to insert this information to node 1. Node 1 stores the last 3 information. It means it has a term index equal to 3. This 30 is going to be 3, and it is completely okay to have 4th index. So for node 1, everything is okay. How about with Node 3? Unfortunately, Node 3 has inconsistent data. It means it has only index 1, but the latest index is going to be 4, and we are missing index 2 and 3. How to deal with this issue? This is our scenarios for implementation. We have Node 4 as a leader. Node 4 is trying to send index 4 to the Node 3. Node 3 has index 1 as a latest information. So we have inconsistent data, inconsistency here. So Node 3 will respond with bad request, with error that, sorry, I cannot accept this entry because I don't have the latest information from the database. In the second scenario, our Node 4 is going to decrement its index to switch the previous index. We'll try to send the previous index. It means it is going to send not index 4, but index 3. Node 3 will respond again that, sorry, my index is not equal to 2. For that reason, I cannot accept index equal to 3. Okay, and then Node 4 is going to decrement its value to 2 and send it to Node 3. And Node 3 has index 1. We are sending index 2. Now everything is okay. Cool. And then for making all the things to be in a consistent mode, the Node 4 is going to send index 3 and index 2 and then index 3 to the Node 3. And at the end, we are going to have all 4 entries in Node 4 and in Node 3. That's actually how the data consistency, we are reaching to the data consistency. Let's talk about the latest thing is about usage, where we are using RAFT as a protocol for distributed consensus. etcd, CockroachDB, YugabyteDB, Cool, MongoDB, RabbitMQ, and of course Apache Kafka. Starting from 4th version, Apache Kafka is going, guys from Apache Kafka is going to remove Zookeeper and will switch completely to RAFT, Kafka RAFT algorithm. Okay, it means we don't have a manager like Zookeeper, and we have one of the broker will be selected as a manager like a Zookeeper. I will handle all the cases. So this is the Apache Kafka is already using RAFT algorithm, but it is actually in a testing mode. It is not ready for the production, and starting from 4th version, it will be ready for production. So that's actually all related to RAFT. I hope I could explain. If you like my video, if you love it, please like and share. So see you in the next tutorial.